last lectures that I talked about. Last time I will talk about one out of two Oblivious transfer protocols, and here is the defense. We have two parties, Alice and Bob. For the input, Alice has x0 and x1. Bob has a b which is in 0 or 1. And after one out of two Oblivious transfer protocols, Bob will get xb from Alice, and Alice got nothing. Last time I used RSA to realize this protocols. And today I will talk about one out of n protocols. It's a tension of 1 out of 2. Here, for Alice have the input n inputs from x1 to xn, and Alice has I which is belong to 1 to n. And at the end of the protocol S, Bob will get xi, and Alice will get nothing. And this protocol is based on the 1 out of 2 protocols. And as I told last time, we can directly to extend RSA to R1 out of n, but as we know, the modular computation is very expensive. And today I will talk some algorithm will reduce the complexity from the complexity of n to log n. It's being reduced. First, I will first review the pseudo-random functions. It's defined as this one. A simple pseudo-random function. This function is the key. We can transfer a binary streams to a pseudo-random streams, and unless you get the key, you cannot break off. I will continue to talk about Alice, the specific of this protocols and Bob. First, Alice will generate here I define the n is equal to this one L 2 to L, and first we'll generate the L pairs of random numbers, which is and L pairs of random numbers, and then for each number is x1 to xn. we implement these computations, and this is the single random functions, and for each I belong to 1 to n, it's I1 to IL is the bit representation of I, and then for each bit it corresponds one random numbers. We can extract for each I, we can extract L random numbers that implement this computation, then get the yi for each xi. It can for each xi we can get the corresponding yi, and but for Bob only he gets this information and implement the XOR operation without getting the random numbers. K, and without getting Ki from KL, you cannot get any information about Xi. So Alice can publish all the number from Y1 to Yi. And send to Bob. Bob have this information, but he cannot know anything about Xi. And but Bob has number of I all of the numbers. Each correspond to Xi. And she has the bits of I is I1 to IL. And for each number, he can use one out of two Oblivious protocol to get the corresponding random numbers from K1, I1 to KL, RL. And this is the bits, the I1 to L is the bits repetition of I. And then he can, Bob can get the random numbers from Alice by one out of two Oblivious protocols, and there are L pairs, so there he just need to implement the L implementation, and so it's L one out of two protocols. L is equal to log n. After get the random number of K1, I1 to KL, he can implement XOR operations called he. This function is just it means, and he gets the seed, and then x1 xi is equal to yi XOR implement and to get the xi, and that's the one out of two of these protocols. In this protocol, Bob used the random functions and based the one or two protocol to implement the one out of n protocols and reduce the complexity from n to log 2 of n. Questions? Oh, for a number z is equal to x or xy, then x also equal to I use this property here. If no question, I will go over application. Go continue. Based on 1 out of n protocol, I will talk a small application. It's called Oblivious Polynomial Evaluation. This protocol says that Alice have polynomials called Py. Py is polynomial and has degree dp. And Bob have number alpha in a field F. And all the computation is implemented in the field F. And Bob want to know the P alpha. But Alice do not want Bob to know the polynomials. Alice just want Bob to know the P alpha. So as the output of the process, at the end of the protocol, Alice learned nothing about alpha, and Bob just learned P alpha, not the exact form of Py. I will use 1 out of n protocol to implement this Oblivious or polynomial evaluation protocol. First, following is the implementation. First, we need to define a security parameter. Okay, the security parameter is the input size of the cryptographic tools. And then, for Alice, we will compute k is equal to dp. Here, dp is the degree of the polynomial py. And then, Alice will generate a random polynomials p called txx, which has degree of d. has these forms, and all the coefficients AI is random numbers, and we will not know to Bob. And the degree D is equal to K multiplied dP. And this polynomial do not have constant terms. So we know that Px0 is equal to 0. Then Alice will hide this random polynomial into a polynomial called Qxy, which has the form of Px x plus Py. This is Qxy, the polynomial Qxy. It has two variables, x and y. And we know that Q0y is equal to Py. From these forms, we can see that these variables. Then for Bob, he will also generate a random polynomials and have degree of k, called Sx. You notice that. This is also polynomials, random polynomials generated by Bob, and is not known to Alice. And Sx have property that S0 is equal to alpha. So the constant term of S is equal to alpha. And the degree is k. Degree equal to k. So after both Alice and Bob defined Qxy and Sx, and we can see that there exists a polynomial called Rx, which is equal to Qx. You can describe.
Sorry, I'm kind of lost. Where's K again?
K is the security parameter. It's defined both by Alice and Bob.
So both of them okay?
Yeah. K is known to both people. Its security parameter is the input size of security tools. Both know each other.
Okay.
For example, you use the ASE, DSE, the security parameter may be 118 or 16. This is the security parameters. So after define the Qxy and the Sx, we can define a polynomial called Rx is equal to Qx, and y is replaced by Sx. And Rx has degree of from this is d. Degree of alpha is d, and Rx has properties R0 is equal to Q0 Q0 and S0. We see that the Q0 here is equal to Py, and X0 is equal to alpha. So the R0 is equal to P alpha. That's value that form you want to know. But this form is we defined, and the exact form not known to both parties here. They just know the abstract forms and know the exact form Rx. So, for Bob, because for Bob, if unless he can learn Rx, then he can compute S0. So for polynomial, if you want to the exact form of a polynomial, you need to, if the degree is d, you need to d plus 1 points to fit in these polynomials. And like that. I want to emphasize that even though Bob knows the exact form of Rx, he cannot learn the form of Py because we have introduced random. We have introduced random number in the polynomials. It cannot because it not know the random number of Py0, so we cannot infer the Py, and it just learn the form of Rx. So Bob need to d plus 1. D plus 1 point, which is equal to here d is I define dr is equal to the degree of r is equal to d. Here. You know this many points. But if A generates some points,
so dr is d. Well, d is dr now. Oh, okay.
D is equal to dr.
Okay.
D equal to dr. Or just we can say it's equal to dr is emphasize the degree of r. And if Bob directly generates the points and some points and then send to Alice and then generate, and if Alice also know the points of S, for example, for Rx, if Alice knows some points from x0, x1, define this equal to y. This y is not the same as this y, it's just one variable. And the y1, xn, yn. If Alice knows this many points, he can also fit in these polynomials and then the P alpha, and they will break the privacy rules. So we cannot let them both to know the polynomials. We just need to know the polynomial, these polynomials. To protect this privacy, we can use the one out of n protocols. Here I define a variable uppercase n is equal to n multiply m. M is the integer, and it can be chosen between Alice and Bob. Here I want to say that m is As a matter of fact, M is the one out of M. I will see the following. Let's see. Now, Bob will generate the big N points. From x1, x big N. And all of the x I is not equal to 0. And then Bob will define a set. Bob will generate the n random numbers from I1 to In, which satisfies this equation. And this meaning I can show you in the plot for the n points, and each interval have m points. That Bob will for each interval this in equation said Bob will choose one random point from each interval. This one random, one random. This was this equation. Then Bob will partition the unpaired x because he generated n points, and he will also generate the unpaired of these points. For each, he will generate for each xi, he will compute the corresponding yi. And yi is defined as this one. If I is equal to the selected points of I1 or In, then it is equal to y is equal to xi here. If I is equal to I can use j here. if J is equal to I1, I2, I1, yi defined as xi, and otherwise it's defined random numbers. You can choose random. So for each point, for each interval, it has 1 point, and which corresponds to xi. Then for each interval, Bob and Alice can implement 1 out of n protocols. If you assign these points, all the points for this interval, all the points to the Bob, and then he selected this point as his return value. By this, by 1 out of n protocols, Alice will learn nothing about the exact form of yi I1 to in, and Bob will have n points of the polynomials. Then Bob can implement polynomial fitting to get the form of Rx, and Alice did nothing. I don't know, because I have used this protocol just in the summer, a long time ago. I'm not sure if you understand that.
Any question?